Yesterday, we introduced inductance. We talked about inductors. We talked about how an inductor could be used as an electromagnet. We talked about how we could take a magnet and move it across the inductor and generate voltage. And I want to do a quick review before we move on and talk some more about inductance and then move over into transformers and power transformers. Who can refresh my memory? Who can give me a basic description of the physical characteristics of a simple inductor? David?
Ferris core?
Okay, it could be wound on a ferrous core. It could also be wound on an air core. We did go over some schematic symbols yesterday. The first one was what, David?
Air core inductor.
Okay, this is an air core inductor. What happens if I take that same symbol
Iron core.
and add two lines to it? Nikki?
Iron core.
Okay, that makes it an iron core inductor. What if we throw an arrow through it, Vince? It becomes a variable inductor. And then I could also add the lines, and then it would be a variable iron core inductor. Now let's talk about physical properties. If you were to describe an inductor, what would it look like? Alonzo?
Tightly wrapped wire.
It would look like a wrapped up coil of wire. It might look like a little spring. We talked about creating inductors as an assignment, and we're going to actually have a little competition and see whose inductor can lift the most weight. And we're going to do that with screws or paper clips or something. Here's a very simple inductor. I'm actually going to pass this around so you can look at it, and I want it to come back. Basically, I took a bolt, and that was doing what David said. David said a core. So we have a ferrous core. What do I mean when I say a ferrous core? It means it has iron in it. It has magnetic properties. It's not like a piece of aluminum where a magnet's not going to attract it or stick to it. It's got a ferrous material in it. It has iron in it. And then I wound the wire up on the screw, and the turns are close together. And I actually put some electrical tape on the end just so it doesn't fall off the screw. I'm going to send this around, or the bolts. I'm going to send this around so you guys can look at it, and then we're going to actually hook it to a power source and see what it does. Now, when constructing an inductor, what are some of the physical principles that determine inductance? Seth?
Like thick wire.
Okay, how thick the wire is. So if I was to make a better inductor, let's say that bolt with those windings on there, I wanted to make the inductor better. I wanted to have more inductance. One of the things I would do is do what Seth did, or stated. Use thicker wire. Thicker wire has less resistance. Less resistance is going to allow more current to flow. And when current flows through our inductor, we know it builds up a magnetic field. If I have more current, I'm going to end up with more magnetism. What can I do? A second thing to physically construct my inductor better. Matt?
Close turns.
Okay. The wire turns need to be as close together as possible. We don't want them far apart. If I want to get more inductance out of my inductor, I want the turns to be really close. That's why we sometimes use enamel wire. Enamel wire is like an enamel paint. It's actually similar to fingernail polish. On the outside of bare wire, it's thinner than that plastic or rubber insulation, thus allowing the turns to get very, very close. So closer turns will give me more inductance. How about another?
Larger diameter core.
Okay, the larger the turns, whether it's on a core or an air core, the larger diameter will give me more inductance. What else? David?
More turns.
More turns. Maybe that inductor has 10 turns of wire. Let's make it 20 turns. It will then have more inductance. And the last one is one of the first things that we said. David said it. We're going to put it on a core. If I have an air core inductor, it creates so much magnetism, electromagnetism. If I slide a ferrous core in there, I'm going to have more. So add or improve our ferrous core. Go down. The unit of inductance is henries. So that's important to remember too. What is the letter symbol for inductance that we talked about yesterday?
L.
The letter L. Okay, so inductors are measured in henries. And the letter symbol for inductance is the letter L. Here's that simple inductor we were passing around. Now we said yesterday that if we hook the inductor to a power source, and I'm going to just use a little 9-volt battery. Here's my inductor. I'm going to take just a couple of paper clips and set them on the bench. We said that when we hook it to power, we're going to hook it to a battery, we're going to get voltage and obviously current. That if you could see it, there would be a magnetic field encapsulating this inductor. Now, as you can see, these paper clips are just laying there. I'm going to hook my battery up, and I picked up 3 of the paper clips with no problem. I disconnect my battery and the paper clips fall. That is a very simple electromagnet. This is what you guys are going to do at home for homework. I'm going to give you all a couple of lengths of wire. I'm going to give you a couple of bolts, nails, some ferrous cores, and I want you to experiment building inductors, and the best inductor that you create is the one that you're going to turn in as a final assignment. And we're going to have a competition, and we're going to see whose inductor lifts the most weight. We'll use paper clips, and we'll see who's actually lifts the most paper clips. Now, where is some of this stuff used? We talked about this yesterday. Give me some uses in the practical, real electronics world. I mean, we're not running around with nuts and bolts and little pieces of wire on and picking paper clips up. Give me some real world examples.
Fire alarms.
Okay, we talked about the fire drill yesterday. That big fire bell that goes ding, ding, ding has an inductor that's moving that mallet that's striking that bell using electromagnetism. Great example. David?
The junkyard with the giant magnetic crane.
That junkyard crane that has that huge electromagnet that goes down and picks up the car and moves it over and drops it. That's a huge electromagnet, but it's nothing but a huge inductor. Very good example.
Electronic locks.
Electronic lock systems, very good. What else? Well, I'm going to show you a couple of things. I'm going to show you a couple of components that you probably haven't seen before. The first one is something very simple. This is called a solenoid. And a solenoid is something that has a lever that moves. Now this solenoid is either going to push or pull. I don't know what direction it's wound in. So when I hook the battery up, it's going to do one or the other. If I have the polarity wrong, I'll flip it and see what happens. But basically what I'm going to do is I'm going to pull this little solenoid out because I believe this is going to pull. See how that pulled in? So if I need to move a latch or a lever, I hit the solenoid, the electromagnetic field builds up and pulls the lever in. I'll pass this around so you can look at it. What's under this black tape is what? A big coil of wire. This will fall out, so let's not lose that. When you energize the coil of wire, it pulls that in. Does that make sense? Taylor? I said don't drop that. But Vince, come on up. On this side of the bench here. This guy here, anybody have an automobile where you push a button and the trunk opens up? This is very basic. There's just a little lever that has to move about a ½ an inch, and that releases the trunk, and it pushes, and a spring loading pushes it up. Pull on that. I don't want you to pull hard. It doesn't have tons of force. Well, not yet. Just kind of hold it there, and then I'm going to pull back. And you should feel this pull. You only have one hand. It's just going to. See how it's pulling?
Yeah.
Do that again. You're pulling too hard. Okay, we lost it. My battery disconnect. There we go. So that's pulling in. Again, it's very similar to that solenoid that we just had. There's a lever in there. It pulls this steel wire, which would undo the trunk latch and allow the trunk to open up. Again, perfect use of electromagnetism. Here's another one, but it's out of a car door. Hook my battery up. Goes in one direction. I'm not sure if this goes in the other, but we'll see in a second. That pulls. If I flip my positive and negative, it pushes. What do you think that is? This is out of a car door.
Wow.
The door lock. Hit your remote. Receiver receives the signal, sends voltage to it. The door either locks or unlocks. Unlock up, lock down. Does that make sense? I'm not going to hook these guys up. These are 24 volts, so I only have a 9-volt battery. This little guy here is a pneumatic controller. This is a valve. Air comes in and air comes out. Hook voltage up to this, the little valve moves and allows air to either turn on or off. Does that make sense? Air is pumped into one side. When it's deactivated, it's like the air valve is turned off. As soon as I put voltage there, it opens up and air blows out the other side. Here's another pneumatic controller. This actually has 4 of these solenoids. So air comes in here, and I can activate 4 things that require air, one at a time, or all 4 at a time, or however many I need, using these solenoids. What is this guy? Alonzo? This is a loudspeaker, an audio speaker to reproduce sound. And we've kind of cut it up here. How does an inductor work with a speaker to create sound? Okay, what is sound?
Air movement.
Very good. Air movement. I'm speaking. Air is coming out of my lungs. It's going over my vocal cords. They're vibrating air molecules that bump into each other. It goes all the way to you. Hits that eardrum in there, and we interpret that as sound. It's an acoustical vibration. Sound, vibrating air molecules, and we hear it. If I can make this big speaker cone go in and out at the same frequency or the same rate that my vocal cords are doing it, I can reproduce sound. So now, what I have to do is take electricity from a power amplifier. I have sound, which we convert into electricity. The electricity will feed the speaker, which causes the speaker to move, causing an acoustical vibration. So basically, if somebody was to speak into a microphone, we're taking acoustical energy, turning it into electronic energy. The microphone turns it into electricity. The amplifier amplifies it, makes it louder, sends it to the speaker, and the speaker's taking the current and voltage from the amplifier and turning it back into acoustical energy. Does that make sense? Okay, now here's what happens in a speaker. I'll send this around in a minute. We have a voice coil. They call it a voice coil. Here's another. It's just a coil of wire, another inductor. The inductor is glued to the cone. So when I move the inductor, the cone moves up and down. So what makes the inductor move? Well, around the inductor is this magnet. So if I have an inductor and voltage and current flows through the inductor, a magnetic field builds up. Now we know if we take 2 magnets, if we start to bring the magnets to each other, what's going to happen? Seth? What's going to happen to the magnets? They're either going to repel or attract, depending on what their poles are. Well, when I have current flowing through the voice coil, I build up a magnetic field. I now have a fixed magnet. So even an electromagnet and a fixed magnet, a permanent magnet, will attract and repel. Now, the voltage coming out of an audio power amplifier is alternating current. So what does that mean? It means it's constantly changing directions. It's going from positive to negative many times a second. So at one point when the magnetic field builds up, it's going to push the cone, and at another point it's going to pull the cone. So it's going to go up and down, vibrating at a high frequency, creating an acoustical vibration that we can hear. Now I'm going to demonstrate it with this really big speaker. Here's one that's not all cut up and still functions. Here's my 9-volt battery. Now we said at one polarity, the speaker's going to push, right? And in the opposite polarity, the speaker is going to pull. So what I'm going to do is I'm going to take this speaker, I'm going to hook up one side of my 9-volt battery, And I'm going to hook up the other side of my 9-volt battery to the voice coil. Now, right now, the speaker's doing what? And if I do it really quick, you can hear it pulsing away. What's going to happen if I reverse the polarity? It's going to push. And actually feel the air coming off the back of the speaker. Come here, Vince. Don't drop the speaker. This is an 18-inch woofer. It's pretty heavy. Put your hand right back there. Tell me what you feel. You feel air movement?
Yeah.
So basically, voltage and current creates an electromagnetic field that's right next to a permanent magnet, and that electromagnetic field is constantly varying. It's building and collapsing and building and collapsing. But remember, it's not doing it as slow as me turning it on. It's doing it hundreds of times a second and thousands of times a second at the rate of human hearing. And that's how it can turn into voices, sound, music, musical instruments. The faster it vibrates, the higher the pitch. The slower it vibrates, the lower the pitch. Absolutely. We also said, and we showed this yesterday on the scope, we took an inductor and we waved a magnet across the inductor. What did we see on our O-scope? What did we see on the oscilloscope? Moving the magnet very quickly back and forth.
It would create the sound.
We actually saw voltage created. So a magnet moving back and forth across an inductor can generate voltage. Now let's talk about how this relates to transformers. Because a transformer is really nothing but two inductors. Now we already said that this is an air core inductor, correct?
Yes.
What happened when we added this?
Iron.
It became an iron core inductor. Now, if I was to wind windings on a metal core, and then take another wire and wind another set of windings on that core, I now created an iron core transformer. David?
Oh, I was about to say what it was.
Okay, that's all right. Now, how is this different than an inductor? Well, let's put current to this inductor. Let's put a battery across my inductor. We know that electrons flow from minus to plus, so current's going to flow through my inductor, and we know that it's going to build up a magnetic field. Correct? Okay. Now, on the other side of the transformer, which is my second inductor, I hook up a sensitive voltmeter or current meter. Something that's going to detect any current in this side of the transformer. What do you think I'm going to see here? Okay, now I want you to rewind to yesterday. If I had my little inductor and my little magnet, let's pretend this battery's a magnet, and it was just sitting still. What did we see on the oscilloscope? We saw nothing. But when I started moving it back and forth really fast, what did we see? We saw it go positive, negative, positive, negative. We actually watched the oscilloscope generate voltage. Or the oscilloscope wasn't generating voltage, the coil of wire was. The oscilloscope was looking at the voltage that was coming out of that, the voltage and current. Because this is DC, the current flows in one direction, we build up a magnetic field, but nothing really ever happens here, because if you remember correctly, yesterday we said the voltage is released when there was a rapid change in magnetism. So when I was going back and forth, that was the equivalent of building up and collapsing my magnetic field. That's when the voltage was released. Let's get rid of the battery, and let's put a source of AC into my transformer. Now AC, we know, starts at 0 volts, smoothly rises positive, then collapses to 0 volts, smoothly rises to negative, and goes back to 0. It's constantly changing polarity. It's going from positive to 0 to negative to 0 to positive to 0 to negative to 0. So we're constantly building up and collapsing a magnetic field. We go in one direction. We build up a magnetic field. It has a north and a south pole. Then we quickly change direction. Now it has a south and a north pole. So we constantly have the polarity changing. So what am I going to see over here?
Voltage generated.
How am I going to see voltage generated? Because didn't we just say that this wire had insulation on it and this wire had insulation on it? So how's it going to be there? You're right. You are right, Chris. How's it getting there?
Magnetic fields.
Okay,
Collapsing.
through the magnetic field. We've always been under this impression that we had to have direct connections with conductors to move voltage, and that's true. But believe it or not, I can get from this side of the transformer to this side of the transformer with no electrical connection. There's no conductors connecting. This is insulated wire wound on a metal core, and then more insulated wire wound on that same metal core. They share the magnetic field, thus the voltage is induced. That's part of the word induction, isn't it? The voltage is induced to the other side of the transformer. Now I keep saying one side and the other side. The transformer actually has, there's terminology that we call it. The side that the power comes in is called the primary. If this is called the primary, what do you think the side that the voltage comes out is called?
Secondary.
The secondary. So now I can take voltage and go from my primary to my secondary without an electrical connection, and I'm doing this through a magnetic field. Now here's what's even cooler about transformers. Now we all watched the Tesla video. We finished watching it yesterday. You learned about how Edison started out with a DC distribution system, and we know it wasn't very good because when you tried to send DC a long distance over a wire, that the resistance of the wire dropped the voltage. Tesla's system started generating high voltage AC, and then when we got it to where we need it, he transformed it to lower voltage AC. And that's why this component is called a transformer. It allows me to transform voltage and currents, AC voltage and currents. I can step up voltage or I can step down voltage. How do we do that? Well, I'm going to redraw my transformer a little bit. And what I'm going to do is I'm going to draw a whole bunch of turns on my primary. Here's my metal core, my ferrous core, and I'm just going to draw a couple of turns on my secondary. When I have a lot of turns on my primary and only a few turns on my secondary, what effect do you think I'm going to have on voltage? Alonzo?
It's gonna bring the voltage from primary down to the amount the secondary has.
Okay, so the primary voltage is going to get stepped down. Now let's say, I'm going to use nice simple numbers. Let's say that there's 100 turns of wire wound on my primary. And let's say that there are 10 turns of wire on my secondary. What would that ratio be?
1 to 10.
Actually, 10 turns to every 1 turn, depending on what side you're looking at. 100 turns and 10 turns, so it's 10 to 1 is what my ratio would be here. So whatever my voltage is here, it's going to get stepped down by 10. Now, what's our wall voltage? What comes out of the outlets in our wall? 120 volts at 60 hertz. So if I have 120 volts AC, and I need to step it down, I'm going to divide this by 10. This will bring it down to 12 volts AC. This could be that little black wall cube that charges your phone. or powers a smaller device. It would require less voltage. We would step the voltage down with a transformer. What if I did the opposite? What if I put less turns on the primary and more turns on the secondary? Dakota, say that louder, please.
It raises the voltage.
Very good. It steps up our voltage. Transformers step up or step down. So raise and lower is correct, but let's use the terminology that we're going to stick with in electronics. Transformers will step up or step down. So in this case, it steps up the voltage. Let's say that I only had a few turns on the primary. And I had many turns on my secondary. And we'll just say it's 10 turns and 100 turns. Now my voltage will be stepped up by a factor of 10. There's 10 turns on the secondary for every 1 turn on the primary. So now I'd have 120 volts in, and I would have 1,200 volts AC out, which is the equivalent of 1.2 kilovolts using our proper engineering notation. So that's a step-up transformer. Now another question for thought. If I can step voltage up, why can't I solve all the world's energy problems?
Because it doesn't change power.
Just keep stepping up voltage.
Because it lowers the current if you step it up.
Okay, very good. Dakota, what did you say?
You can't change the power. Power's constant.
Okay, you can't change the power. And John, what were you going to say? Pretty much the same thing? Or?
I was
Okay.
just saying it's filter.
Here's the thing. If my voltage goes up by 10, what do you think happened to my current? It went down by a factor of 10 in most cases. If I use really thin wire on the secondary, it can go down by even more. So let's do Ohm's law. If I have 120 volts and under load my transformer is drawing 1 amp of current, we know that 120 times 1 would be 120 watts. That's what our power law says, right? Well, I don't have 1200 volts at 1 amp anymore. I now have 1200 volts at 100 milliamps. 1200 volts times 0.1 amps, which still gives me 120 watts. So unfortunately, as Dakota said, I can't transform power. I can always lose power, but I can't gain power. If we could figure out how to make the transformer gain power, even if it was a little bit, we would just feed a transformer into another transformer, and we would have all the power we need. We're not going to solve the energy crisis in high school electronics today. I'm sorry, guys. I wish it was that simple. Now let's throw a couple other monkey wrenches in the works here. I'm going to clean the board up a little bit. Let's get rid of some of this clutter. You guys have for your notes primary and secondary. I can erase this. I'm going to use nice round numbers again. We're going to stick with 100 turns. On my primary, and we're going to stick with 10 turns on my secondary. I have 120 volts coming in. I have 11.8 volts coming out. Now we said that when we have a 10-to-1 step-down ratio, I'm going to divide by 10. So 120 volts would be stepped down by a factor of 10, which should have gave me 12 volts. But in the real world, I don't get 12 volts. I get a little less. Why? Why do I get a little less?
Some gets lost in heat in the wire.
Okay, whenever we have power loss, that's good. It is typically lost in the form of heat, but where did the loss occur? You're right, Dakota. You're on the right path. In the wire itself. Didn't we say that copper wire does have resistance? While it's a really good conductor of electricity, it does have some resistance. And when we start winding up hundreds of turns of wire, we got a few feet of wire here. So it can add some resistance to my circuit. So I have resistive losses, or what we call copper losses in my transformer. Some people call it copper loss. Some people call it resistive or resistor loss. Resistance in the wire. What other kind of loss could occur? That is one of our main losses. What other kind of loss could occur? What if I used pure refined iron versus like regular steel? Do you think one core might be better than another core? Some cores will have better properties than other cores. So we can actually have core losses. Depending on the material that the core is made of, some cores will transfer energy from the primary to the secondary better than others, depending on what type of core material we use. So we can have core losses. What else? I'm going to throw a word at you that some of you may have heard and some of you may have not. I might even spell it wrong. Hyster, hysteresis. I think I spelled it right. Hysteresis. Hysteresis loss. Does anybody know what hysteresis loss is? Or does anybody know what hysteresis is? Okay, hysteresis is the ability of a core to retain magnetism. Now, has anybody ever taken a magnet and then taken a screwdriver and you rub it across the magnet real fast, back and forth, and then you magnetize your screwdriver? Who's done that? Okay, what happens a couple of days later, Mira?
It
Goes back to a regular screwdriver. It's no longer magnetic. The more metal retains magnetism, the more hysteresis loss we have. So if I'm constantly building up and collapsing and building up and collapsing a magnetic field around this ferrous core, that core is going to retain some of that magnetism. Now, when my magnetic field is building up and collapsing, remember I used the example of two permanent magnets. When I bring them together, they want to repel, right? Well, when we have those like poles, that hysteresis wants to repel that magnetic field a little bit, causing a little bit of loss. Does that make sense? That's a situation where we do what we call a laminated core. The metal core is actually sliced up into thin sheets of steel. Then they actually paint them, and then they put them together. So sandwiching all these insulated pieces of metal together makes it retain less magnetism, giving me a more efficient transformer that has less core loss. Does this make sense? How about eddy current losses? What is an eddy current? What's an eddy current in the ocean? Okay, who's man enough or woman enough to admit that they play with a rubber ducky in the bathtub? Little boats floating around? Okay. John playing with a little rubber ducky in the bathtub. He's got G.I. Joe in there too. Okay? G.I. Joe's floating around in his boat, and he's making waves in the tub. So we got these waves going. Then the wave hits the side of the tub. What happens? It reflects back. And then when the crest or the peak of a wave hits each other, it kind of knocks it down. That's an eddy current. Well, again, we have some retained magnetism because of hysteresis. We also have these currents in the transformer that are building up and collapsing and building up and collapsing, and these magnetic fields that are building up and collapsing. And then voltage real quick changes, and we got another build up and collapse. So we end up with some of these eddy currents and these magnetic fields and these voltages that are constantly changing direction and doing all these other things that are bumping heads and causing some more cancellation. That's called an eddy current loss. So our transformers are not perfect. If I have 100 turns on one side and 10 turns on the other, I do not end up with an exact 10-to-1 ratio. 120 volts comes in, I don't necessarily get 12 volts out. I'm going to lose a little bit of voltage because of copper, core, hysteresis, and eddy current losses. There are main losses. Who's got questions about transformers? So you're all experts? Good, I'm just going to get a test now. I'm kidding. I'm going to pass a couple out a little bit, then you can look at it and you'll be able to see the laminated core and things like that. This is a power transformer out of a microwave oven. This is our primary, this is our big core, and this is our secondary. The primary is made of thicker wire with much less windings. The secondary has a whole lot more windings, but it's much thinner wire because the current's going to be stepped down as the voltage goes up proportionately. If you look closely, you'll see all these lines in the core. That's the laminated core. This was sliced up, painted, put back together, and welded together. That's our laminated core, which minimizes hysteresis loss.